Welcome to This Explainer. Okay, today we are unpacking something absolutely fascinating, the mechanics of how machines actually think, operate, and make decisions in the real world. You know, we interact with robotics constantly, literally every day, but we rarely stop to ask, hey, what's actually giving this machine its precise instructions? So we're going to examine the entire spectrum of control, starting from pure human-driven teleoperation all the way up to complete robotic independence. Let's get right into it.
Okay, let's dive into this with Section 1, the Mars joystick problem, or why remote control just completely fails in space. Think about this for a second. How do you actually drive a rover on Mars? Down here on Earth, we're super accustomed to instantaneous feedback loops, right? You're playing a video game, you push a joystick forward, and bam, your character moves immediately. But trying to apply that real-time, video game-style control to a vehicle like the Mars rover Sojourner, which is sitting millions and millions of miles away, yeah, that completely breaks down.
The massive roadblock here is signal delay. Because of that gigantic communication gap between Earth and Mars, NASA couldn't just drive the Sojourner rover. It just doesn't work. A command sent from Earth takes minutes to travel through space. And getting the video feedback confirming the rover actually moved, that takes just as long. So by the time you realize the rover is, say, heading right off a Martian cliff, it is way, way too late to hit the brakes. This massive delay makes real-time remote control literally impossible. It dictates that the machine absolutely must possess its own independent machine logic just to survive. Basically, it strictly requires autonomy.
Which brings us to Section 2, teleoperation and human safety. Let's talk about the human element.
Before we get to full independence, we really need to look at systems that still rely entirely on us. We're looking at the two absolute extremes of robotic control here. On one side, you've got teleoperation, which is completely human-led. Every single action the machine takes is explicitly commanded by a person. And then, all the way over on the other extreme, we have autonomy, an entirely robot-led system where the machine is making its own decisions based on its environment and its programming. Understanding the tension between these two poles, that's the key to the whole shebang in modern robotics.
To define teleoperation clearly, I want you to use an easy mental shortcut. Think of a telerobot as relying on a man behind the curtain. The machine itself might look like it's acting on its own, doing its own thing, but there's always a human pulling the levers and pushing the buttons behind the scenes, dictating every single move it makes.
So, why do we even deploy telerobots if we have autonomous tech? Well, bomb sniffing and bomb disposal units are actually perfect examples. We use them specifically because they prioritize human safety in incredibly dangerous situations. The human operator gets to stay back at a safe distance, making all those complex, really high-stakes decisions, while the machine acts as a physical avatar right there in the hazardous environment. The robot takes on the physical risk, but the human retains total 100% control. Moving right along to Section 3, stepping up to autonomy, and how we bridge the gap.
See, crossing that bridge from human control to autonomy actually happens in very distinct stages. Let's walk through them. First, you have manual control via Bluetooth. This is your basic teleoperation, just like a remote control car. Step 2 introduces programmed paths, kind of like commanding a robot to drive in a perfect square. Now the robot executes a set of instructions without someone live on the joystick, but it's still just blindly following a script. Step 3, though? Step 3 is the real leap, adding an avoid obstacle sensor override. So now, if the robot is driving its programmed square and a rock blocks its path, its hardware and programming actually allow it to override that original instruction to prevent a crash. Taking action like that without direct human intervention, that is the exact birth of semi-autonomy.
Now, I want to pause for a second and ask a slightly philosophical, but honestly very practical question. If a robot is fully autonomous, making its own decisions, doing its own thing, but its batteries die, is it still independent? It really forces us to actively engage with the true definition of independence. Because no matter how incredibly advanced a machine's independent logic is, at the end of the day, it is ultimately bound by its physical hardware and its power source.
Okay, Section 4, dispelling robot misconceptions, separating fact from fiction.
This distinction is absolutely critical to internalize. When a machine is classified as autonomous, it simply means it operates using independent machine logic. Its complex programming and its hardware allow it to function without direct human intervention. It absolutely 100% does not mean the robot possesses a soul or has feelings. We have to clearly separate science fiction from science fact here.
Autonomy is an incredible, mind-blowing feat of engineering, logic, and sensor overrides, but it is not the spark of consciousness.
Section 5. Classifying our robot world. Putting it to the test. Now, what's really interesting about this next part is mapping our everyday machines onto this spectrum.
Let's actually put this theory into practice and classify some everyday machines based on their level of independence. Think about a remote control toy car that is strictly teleoperated. Moving up the spectrum, something like a Roomba vacuum or a modern drone introduces semi-autonomous features, things like self-stabilization, hovering, or basic obstacle avoidance. Then you have an industrial arm on an assembly line, which heavily relies on blind, programmed tasks. But a Mars rover like the Sojourner we talked about, that relies heavily on autonomous logic just to survive those massive deep space communication gaps. It's the programming and the hardware that precisely dictate which functional category a machine falls into.
All right, let's quickly recap to really cement everything we've covered today. Going way back to our initial hook, true or false, the Mars rover Sojourner was a purely remote-controlled teleoperation mission. Well, the answer, of course, is false. As we've established today, it is completely true that Sojourner had to use independent logic and autonomy precisely because of those huge, unavoidable signal delays between Earth and Mars.
To wrap up our explainer today, I want you to consider this thought-provoking little reflection. If you were a robot, would you rather be perfectly teleoperated by an expert, safe, flawlessly guided, with a man behind the curtain? Or would you rather be fully autonomous, out there making your own decisions and facing obstacles completely on your own? Really think about what control and independence mean, not just for machines, but conceptually for us too. Thank you so much for joining me to explore the spectrum of autonomy today, and I will see you in the next explainer.